Okay, I'd like to kind of again summarize where we are. So, summary of what we know is about as follows. From the stuff in 3.2, we know that we expect two-dimensional solutions, or two-dimensional family of solutions to second-order linear homogeneous equations. We can check if we have the full family in the form C1 y1 plus C2 y2, where L of yi is equal to 0. How do we check whether this is the full family? Sorry, I didn't hear you all. So how do I check if I have the full family given by two particular solutions, y1 and y2, to a second order linear homogeneous equation?
You check the Wronski?
Yeah, via the Wronskian. Namely, w of y1, y2 not being the zero function is not the zero function. So as long as the Wronskian is not the zero function, then you have the full family written out this way. You can, any solution to any IVP can be written as C1 y1 plus C2 y2 for some choice of constants y1 and y2 for your pair of solutions. And then we are starting to examine the most simple second order, the most simple second order linear homogeneous equations, namely the ones with constant coefficients. So we consider a y double prime plus by prime plus cy being equal to 0. And so we already know what to expect from the solutions. So associated to this is the characteristic polynomial. Ax squared plus bx plus c. So there are kind of three parts. Part one, what if this polynomial has two distinct roots, say R1 and R2? Then what do we expect for the solutions to this differential equation?
It would become, well, C1 times e to R1 times t, then plus C2 e to the power of R2 times t.
Exactly. So the general solution will be C1 e to the R1t plus C2 e to the R2t. This is our general solution, and if you're asked to find a specific solution to an IVP, then you'll essentially plug in and be solving a linear system. Okay, so we did this now like 3 or 4 days ago, so I think we're pretty satisfied with what happens in the two-root case, right? Any questions on anything that I've listed so far? No? Okay. The second case is that there are two, this is distinct real roots, sorry. Distinct real roots. Let's assume now that the roots of the characteristic polynomial are a plus bi and a minus bi, right? We know that if there's one complex root, then the other root of the polynomial has to be its complex conjugate. So the roots have to be like this. What do we know in this situation? So we expect C1 e to the a plus bi times t to be a solution, right? Or at least we know that this is a solution just because this is a root of the polynomial. So when I take derivatives, I'll get 0. Or so we know this is a solution. What do we do further?
We can use rules of exponents to simplify.
Yeah, we use our rules of exponents to simplify. So maybe I'll forget the C1 and I'll just write this is equal to e to the at times e to the I times bt, right? And what is e to the I bt?
E to the I plus e to the bt.
Yes, but I think the thing that we want to do here is use the Euler formula so that we can express, like we want to re-express this purely imaginary term in terms of cosines and sines, which we're able to do via Euler's formula.
Right, it'd be cosine bt plus sine I bt, or I sine
Exactly.
bt.
Exactly. So this whole expression becomes e to the at times cosine of bt plus I sine of bt. Very good. And then what's the last theorem that we use to ensure that we actually get two solutions out of this?
Sorry, can you repeat the question?
Right. So as I've written it, this is one solution. And what I want is I want the full family of solutions. So I need at least two solutions. Right now I've written one complex solution. What can I do to the one complex solution to get two real solutions?
You can distribute the e to the at and then separate the cosine and sine terms.
Exactly. So maybe I'll write it as follows. If u of t plus iv of t is a complex solution to a second order linear homogeneous IVP, then so is u of t and v of t separately. Oh, you can't see it. There we go. If I have one complex solution such that the real part and the complex part are both non-trivial functions in terms of time, then I get two solutions out of it. And in this case, what this one complex solution gives me is two real solutions, namely e to the at cosine of bt. This is going to be one solution. And then the other solution is going to be e to the at sine of bt. Now, in order to check that I get a full family of solutions from these two solutions, one needs to check the Wronskian. But yesterday we discussed that the Wronskian of solutions of this type will always be non-trivial. In fact, it'll be something like e to the negative 2at. So what we get is that C1 e to the at, oh, question? No question? Okay. These two, when you produce these two solutions in this fashion from a polynomial with complex conjugate roots, these two will always be a fundamental system. So we always get our general solution like this. So let me write like stars. Here, this is a general solution in one case. Here is a general solution in the second case.
If we were given a problem like with complex roots on a test, would you want us to check the Wronskian, or would you could we just assume that we've like already done that?
No, I think that for these problems, I just am going to assume that we have covered that in class. And so you can use the fact that the Wronskian of these two solutions will always be non-trivial, and that's fine. However, I probably will ask you to compute some sort of Wronskian on the test, but I should be explicit about it, or like that should be clear. And if it's only a polynomial with complex conjugate coefficients, then you don't need to check it.
Okay, thank you.
Yeah, sure. Okay, so any questions on this kind of summary that I have right now? No questions. Okay, so what I'm going to do is first point out an interesting sort of side note, and then we'll move on to the third case. So today what I'm going to do is first Euler equations, which are a little bit expanding on what we can cover here, and then we'll do the third case. What's the third possibility for a degree 2 polynomial in terms of its roots?
Repeated roots.
Yeah, third case is a real repeated root. So we'll get to this today. But first I want to cover Euler equations. So let's get into it. So as a side note, thus far, we have really only discussed concretely second order linear homogeneous differential equations of the form a y double prime plus by prime plus cy is equal to 0, right? These are the ones that we're working on solving concretely. However, we should remark the following. If we can find a change of variables such that we get such an equation, we can solve it explicitly. What I mean is that a general second order linear homogeneous, wow, it's such a mouthful to say these things every time. But a general such equation will have functions of t as coefficients, right? A should be a function of t, B should be a function of t, and C should be a function of t. And in general, we don't know how to handle those problems at this point. And generally, those become very, very difficult differential equations to solve. But my point is, if you can find some change of coordinates such that when you perform that change of coordinates, these functions become constants, then we can solve them here and kind of go back. So the example that I want to discuss is the following. Example. So what we're going to look at is the differential equation given by t squared d squared y over dt squared plus alpha t dy over dt plus beta times y is equal to 0. Here we'll assume that t is greater than 0 and that alpha and beta are constants. Okay, so the first remark is that this is quite different from any of the differential equations that we have tried to solve recently, because the coefficients are functions of t now, non-trivial functions of t. They're not just constants. The thing that is special about this particular form of differential equation is that there is a transformation that we can make, a change of coordinates, so that this differential equation becomes one where the coefficients are linear. So the idea, change coordinates. This is very similar to when you were doing integrals in Calc 3. And in some cases, you found that if you changed the coordinates of your integration, or you essentially changed the Jacobian, you could all of a sudden compute integrals that you couldn't compute otherwise. It's a kind of a similar thing that's going to happen here. So for this particular class of equation, and I mean really something very specific here, t squared plus t squared is the first coordinate, alpha t is the second coordinate, b is the third coordinate, we can make the following change of coordinates. We can set x to be equal to natural log of t. Okay? So what I want to do is, if I have this differential equation and I have x is equal to natural log of t, then I want to rewrite all of my dy dt's and dy squareds dt squareds in terms of dy dx's and dy squared dx squared. Right? I need to rewrite this equation so that it's a differential equation differentiating y with respect to x instead of with respect to t. Right? I need to rewrite this equation. So in particular, I need to write dy over dt in terms of dx over dt, and similarly for d squared y over dx or dt squared in terms of possibly d squared y over dx squared. So do you understand what I'm trying to do here? Are there any questions about what I'm trying to accomplish? Okay.
Sense.
Oh, yes. Yep.
Just saying, makes sense.
Okay, great. So essentially, the way that we write these functions in terms of these functions, or sorry, dy dx, this should be. The way that we do this is by chain rule. So for instance, I know that dy over dt, what should this be equal to by the chain rule if I'm deciding that y is now a function of x and x is a function of t?
Would it equal dy dx dt dx or something?
Yes. So the way to remember the chain rule is that the term should kind of cancel if you imagine it as a fraction, right? So we're going to have dy dx times dx dt, and even though this isn't technically allowed, you could imagine canceling the dx and getting back the dy dt. That's how I remember the chain rule. So this is fine, right?
Yes.
In particular, now I can ask literally, what is dx dt?
One over t.
Very good, 1 over t. So we'll use that later. The next thing that I want to write is I want to write d squared of y over dt squared. Well, this is the same thing as d over dt of dy over dt, right? You agree?
Yeah.
But this is equal to d over dt of this expression that I have up here for dy dt. dy dx times dx dt. What's my next step?
Do you chain rule again?
I think I need to do the product rule first. Exactly. Product rule and then chain rule. So the product rule says that this is going to be equal to d over dt of dy over dx times dx dt plus dy over dx times d over dt of dx over dt. You agree? Are you okay with this application of the product rule?
Yeah.
Great. Now let's simplify further. This is kind of a, it's not actually bad at all. The symbols just make it look like we're doing something a little scary. dy dx. This is when I'm writing, this is some function in terms of x, right? I've written y as a function of x, so dy dx is some function of x. How do I take the t derivative of a function in terms of x? This should be the chain rule again, right? This is a function of x. X is a function of t. How do I take the t derivative of this function of x? Well, first you take the x derivative of this function times the dependence of x on t. Chain rule again. Well, I need to take the x derivative here. So d over dx of dy over dx times, now I need to multiply by dx over dt. Here's a function of x, and I need to multiply by the dependence of x on t, times dx over dt, plus, over here, this is already done. This is just dy over dx times d squared of x with respect to dt squared. Okay, so this is sufficient, but now let's be explicit like I asked you before. What is dx dt?
1 over t.
Yeah, so this is dy dx times 1 over t. This down here is going to be, well, this term is the second derivative of y with respect to x. So d squared y over dx squared times dx dt times dx dt. So this is times 1 over t squared plus dy dx. What is the second derivative of x with respect to t?
Negative 1 over t squared.
Yeah, negative 1 over t squared. Negative 1 over t squared. So that was a fair amount of work, but now I can just plug in these expressions, and whenever I see a dy squared dt squared, which is just this one point, I'm going to plug in this equation, and where I see dy dt, I'm going to plug in this equation. And the thing that you already have noticed probably is that the t squared in the numerator here will cancel with the t squareds in the denominator here, and the t in the numerator here will cancel with the t in the denominator over here. So when I plug in, I get the new differential equation. Now, in terms of dy dx, this differential equation, which you can't see, this differential equation becomes the following differential equation. It becomes d squared y over dx squared plus alpha minus 1 dy over dx plus beta of y is equal to 0. This alpha minus 1 comes from the fact that there's a dy dx term inside the dy squared dx squared term, right? When I multiply this expression by t squared, I'm going to pick up a negative 1 times dy dx. So I get a negative 1 times dy dx. Any questions on this change of coordinates that's just been done?
This only works if we have like a differential equation following that exact.
Yeah, this is very
format.
specific. It has to be like okay. The idea of changing coordinates is very general. And there are many changes of coordinates that you can try to do to make such a differential equation into something more tractable. But if you want to use this explicit change of coordinates, then this explicit change of coordinates only work when you explicitly have a t squared times the second order term plus a constant times t times the first order term plus a constant times the 0th order term. So yeah, this isn't some big expansion of the equations you can handle. It's a very small collection of new things that you can handle.
Will it still work if alpha or beta are 0?
Yep. Those are just constants. Okay. Now, what do we know about this equation?
We can use the roots.
Yeah, we can solve this. In terms of roots. And we'll get solutions y1 of x and y2 of x, right? Because now this is a differential equation where y is a function of x. So my solution 1 will look like y1 of x is equal to e to the r1 x, and here it'll be e to the r2 x, right? These are our two solutions. And then the last point that I want to mention is that, oh, now I have to do new things. So if y1 of x and y2 of x solve the diffie-q d squared of y dx squared plus alpha minus 1 dy over dx plus beta y is equal to 0, how can I recover solutions for the initial differential equation? Then does anyone know how I should modify these solutions to recover solutions of my initial differential equation?
You just make it a function of the natural log of t.
Exactly. I just remember that x is equal to natural log of t. So y1 of natural log of t and y2 of natural log of t solve the original differential equation. Any questions about this process? So I think that the challenging part of this process is checking exactly what the change of coordinates does, right? This required not difficult work, but it looked a little messy and it wasn't clear that we were going to get something good. But now you can essentially solve these problems very quickly. Whenever you have a problem of this form, you immediately switch it to a differential equation of this form, solve this like you know how, and then you recover your solutions to your original problem using these two different solutions. So what I would like for you to do is do the following example. Please solve or find the general solution to t squared y double prime plus t y prime plus y is equal to 0. Why don't you give this one a shot, just using this technique that we've introduced. So under our change of variables, what does this equation become?
D
You second
squared
derivative.
y dx squared plus y.
Yep. The coefficient of ty prime is 1, and we know that in the change of coordinates, we get alpha minus 1, so this is exactly the differential equation that results. So just kind of following along slowly. What are the roots to the characteristic polynomial here? The characteristic polynomial is x squared plus 1, right? Or I should use a different variable now. How about z squared plus 1 is the characteristic polynomial, and what are its roots?
2i and negative 2i.
I don't know if we have 2's in there. Shouldn't we just have i's?
Yeah, just i's, my bad.
That's all good. So the roots are I and negative I. And so if we pick a solution, e to the it, this should give us, or sorry, this is now a solution e to the ix. What two solutions do I get from this one complex solution? By Euler's equation, what is this?
Cosine x plus I sine x.
Exactly. Cosine of x plus I sine x by Euler's equation. By the way, I'm sure you know this by now, but Euler, E-U-L-E-R, is pronounced Euler. I was Swiss, so just remember that. And from this one complex equation, what are the two solutions that we get, or the two real solutions in terms of x that we get?
Cosine x and sine x.
Yeah, cosine of x and sine x are a fundamental system. Now, what's the last thing that we need to do to get a fundamental system in terms of t?
Replace all the x's with the natural log of t.
Exactly. Thus, c1 cosine of natural log of t plus c2 sine of natural log of t are solutions, or is the general solution. To whatever this was, t squared y double prime plus ty prime plus y is equal to 0. So this is kind of cool, you know. I mean, perhaps this shows you. It's kind of like in calculus, where every single time that you had a differentiation rule, you could have an associated chain rule, or not an associated chain rule, an associated integration rule. And so Then, if you want to play a game of finding new weird equations that you can integrate, you find some equation which is a disguised version of the image of one of the derivative rules, and then you can integrate. Here, what you could do is you could say, well, I know that I can find solutions to second-order linear differential equations where they have constant coefficients. And now I can try to check all of the possible changes of coordinates from a linear system of equations with constant coefficients to a second-order linear homogeneous differential equation with some kind of wacky coefficients. And I get these wacky coefficients from the coordinate change. Now I know how to find solutions of those, right? Like you could pick any function as a change of coordinates, like x is equal to natural log of t, and then start with a differential equation just in terms of dx's and constants, and see what this equation becomes under your change of coordinates, and voila, you have a new class of differential equations in terms of t that you can solve, if you kind of want to work backwards, so to speak. But anyways, I think that it's important to note that anytime that we solve something just for these second-order linear homogeneous differential equations, that actually implies that we can solve a broader class of equations, but not very much broader. It's however you can get to this class of equations using changes of coordinates.
Does the equation, the original equation, does the coefficient of the y double prime have to be t squared? Or
Yes, it does have to be t squared.
If, let's say if it was like t cubed, can you do the whole divide everything and like try to manipulate it to get in that form?
My guess is that if you had a t cubed out front, you'd also need a t squared in front of the dy dx and a t in front of the y, right? If you multiply the whole equation by t, then you could probably make this technique work. But if you change the coefficient of dy dt to t cubed, but you don't change the other coefficients, then the change of coordinates won't take that equation to a second-order linear homogeneous where the coefficients are constants.
Okay, I think I understand what you're saying. I'm just saying in terms of the original equation that you're given before you do anything, can you manipulate it to get in this form?
If you can, right. So what I'm saying is we just solved this equation and we know how to solve this kind of equation. If you have a t cubed y double prime plus t squared, alpha t squared y prime plus t beta is equal to 0, then this you can also solve in the same way, because just assume t is not equal to 0 and then divide everywhere by t, and you'll get back to this kind of differential equation. So these things, or t to the k times t squared y double prime plus alpha t plus beta y, all these we can solve now.
Okay.
But we cannot solve t cubed y double prime plus alpha t y prime plus beta y is equal to 0, because our change of coordinates doesn't take this differential equation into a differential equation in terms of x where all the coefficients are constants.
Okay, thank you.
Yeah, sure. Good question. Okay, so this was kind of an excursion. What we should do now is investigate the last case where we have a degree 2 linear homogeneous polynomial, or linear degree 2 homogeneous differential equation. So last case, the characteristic equation. So this is section 3.4. The last case is the characteristic equation has a real repeated root. if I have something like ay double prime plus by prime plus cy is equal to 0 with characteristic equation x squared plus bx plus c, what is the condition on a, b, and c so that I have a real repeated root?
B squared minus 4ac is 0.
Exactly. So the general solution, or the general roots of this, are given by negative b plus or minus the square root of b squared minus 4ac all over 2a. We get a real repeated root. Well, this will always give me two numbers unless the plus this and the minus this are the same, which means that this quantity needs to be 0. So we get a real repeated root when b squared minus 4ac is equal to 0, or b squared is equal to 4ac. And if this is the case, what is the real repeated root?
Negative b over 2a.
Exactly. The root is negative b over 2a. All right, you just plug in 0 here and you get negative b over 2a as your root. Okay, so what do we immediately get from finding one of the roots of our polynomial? Whenever I get a root, I can make a solution, right?
Yeah.
Thus, a solution is e to the negative b over 2a times t. This has to be a solution because this is a root. And we, in our very first analysis of this differential equation, we found that whenever we have a root of the polynomial in front of t, this differential equation, when you plug everything in, it'll be 0. It has to be. So a solution is e to the negative b over 2a times t.
Do we have issues with like linear dependence here?
Well, in what sense are you asking about linear dependence? Because we've only gotten one solution thus far.
All right, I was just thinking maybe if like another solution was impossible, but I might be getting ahead of myself.
So it's not the case that another solution is impossible. It just won't be of this precise form.
Okay, thank you.
Yeah. So the point is, once you've got a solution, you can try to hunt down a second solution. So idea, can we use solution 1 to obtain a solution 2 such that the Wronskian of y1 and y2 is not the 0 function? So maybe I'll write of t that's not equal 0 to remind you that the Wronskian is a function of t. I just don't need it to be the 0 function. It can be 0 at certain points of t, just can't be uniformly 0. And there are two ways to go about this. One is an idea of d'Alembert, which is very naive. Idea could v of t times y1 of t be a solution? Where here v of t is just some arbitrary function that you try to solve for. This is just like a super, super naive way to try to find the second solution. There's actually a much more clever way to find the second solution in this case. More clever. Here, we could try to find a second solution via the Wronskian. Right? Remember that it's easier to compute the Wronskian of a second order linear homogeneous differential equation. In fact, we can do it pretty generally, right? As we showed maybe a couple days back, last week, computing the Wronskian of a differential equation is actually pretty easy. And if you have one of the solutions, then you're essentially saying, you know, find y2 such that det of y1 prime, and then y2 prime is equal to w of y1, y2, right? So this thing you know up to a constant. This thing you already know because you've got one solution. Sorry, you kind of can't see what I'm doing. This information you already know because we assume that we have a solution. This equation you already know because you can just compute this in terms of antiderivatives of p of t, the coefficient on the first order term. And so you can try to use this formulation to produce a second function which satisfies the Wronskian. So this is a clever idea that maybe you'll get to explore a little bit in the homework. But a more basic idea, which we'll examine now, is just if I've got one solution y1 of t, I should just multiply this by some arbitrary function v of t and see if that's a solution. Any questions about these two approaches or ideas? Okay, let's try idea one. And it's funny because differential equations is full of this, where the only thing that we can kind of really succeed in are sometimes just the most naive, silly ideas that end up being this huge chunk of the possible differential equations we can solve. Okay. So let's assume that we have a differential equation that looks like y double prime of t plus p of t. Well, let me go back to something of this form. A y double prime plus b y prime plus cy is equal to 0. So we're back in the situation that we know and love. Constants in front of our y double prime, our y prime, and our y. And assume y1 is a solution. Now we want to check when v of t times y1 of t is a solution. Where here v of t is supposed to be some other non-trivial function. Okay, well, how do we assert or how do we check that this thing is a solution?
If you do the determinant of like that and its derivative with y1, you get a non-zero function.
Well, just checking the determinant will give you a whole bunch of functions which are linearly independent in a suitable way, but that doesn't actually force that solution to be, it doesn't force that function to be a solution of the differential equation. How would I check that this thing is a solution to the differential equation?
Could you just plug it in?
Yeah, I should just plug it in. Plug in. So we're going to get a lot of terms, but the second derivative here, we're going to have to do 2 copies of the product rule, but we eventually get a, well, let me write, a v of t times y1 of t double prime plus b v of t y1 of t prime plus c times v of t y1 of t is supposed to be 0. When I write this all out, if I expand, I'm going to get a times v double prime of t y1 of t plus 2 v prime of t y1 prime of t plus v of t y1 double prime of t plus b times v prime of t y1 of t plus v of t y1 prime of t plus c v of t y1 of t is equal to 0. Okay, so it should be more or less clear here that in general, this is hopeless. So hopeless in general. But here's the special condition that we should look for. If this expression up here, let's examine this. If y prime of t or y of t, y prime of t, and y double prime of t kind of look alike, then we could try to collect terms and get a differential equation for v. If y1 of t, y1 prime of t, and y1 double prime of t look sufficiently alike, then we could try to collect terms. And get a reasonable second order linear Diffie-Q for v of t. Right? So what I'm saying is this equation, as it stands, looks pretty terrible. And it looks like you've got no chance of finding a v that makes all of this work. But if these terms look, if all the derivatives of y, say, only differ from each other by a constant, then we have a chance of collecting terms and getting a nice differential equation in terms of v. So let's do an example. So to show you that this actually does tend to work when we've got these constant coefficient second order linear differential equations. And once again, I want to reinforce how naive this idea is. This is like the most basic thing to try, and it almost never works. But for these special simple differential equations, it happens to work. So here's an example. Let's consider y double prime minus 2y prime plus y being equal to 0. What's the characteristic equation of this differential equation?
X squared minus 2x plus 1 equals 0.
0, good. What are the roots?
X minus 1 and x minus 1.
X minus 1 squared is equal to 0. So what this says is that I know I can produce one solution, which is just e to the t, right? E to the t solves this differential equation because 1 is a root of this differential equation, so I've got e to the root times t. This is solution 1. y1 is equal to e to the t. Now, let's plug in v of t, e to the t, and see if we get a nice differential equation in terms of v of t that we could solve. See if we can find a good v of t. So in this case, what is the second derivative of this function?
E to the t. Oh wait, there's a lot of other stuff.
Yeah, it's going to be a little long, so I'll just write it really quick. will be v double prime of t times e to the t plus 2 v prime of t e to the t plus v of t e to the t. Notice this satisfies what I was saying in the sense that all of the derivatives look alike. In fact, all the derivatives are the same. I've picked the nicest possible case where the derivatives literally are just the original function. Minus 2 times, and now what do I get here? The first derivative of this function is going to be v prime of t e to the t plus v of t e to the t plus v of t e to the t. Yeah, plus one of those is equal to 0. What can I do now?
Try to combine like terms.
Exactly, we should combine like terms. First of all, I've got a 2v prime e of t over here. And what do I have over here?
A negative 2v prime.
A negative 2v prime of t e to the t. So this will cancel with this. Over here, I've got one copy of v of t e to the t. Over here, I've got negative 2 copies of it. And over here, I've got another copy. So these 3 terms will cancel. This term and this term and this term. All of these will cancel. This is horrible notation, but hopefully this is clear what's going on, right? I've got 2 v of t e to the t plus negative 2 times v of t e to the t.
Yeah.
So is there a question? No
That-
questions? Oh,
Computed?
sorry, could you repeat that?
Where are you getting the 2 for the first v of t e to the t?
This one?
No, the other one.
This one?
Yeah, is that 2 distributed out fully?
Yeah, so this just comes from the fact that I'm doing 2 copies of the chain rule, or not 2 copies of the product rule, right? So I can do this computation up here. The first derivative of v of t e to the t prime is equal to v prime of t e to the t plus v of t e to the t. And now if I take another derivative of this thing, then I'm going to get 4 terms. I'm going to get v double prime of t e to the t plus v prime of t e to the t. Now I take derivatives over here, plus v prime t e to the t plus v of t e to the t, and I just combine these 2 terms.
Okay.
So I was skipping steps on this taking of derivatives, but I do get a 2 here. Is that okay? Yes, that's okay. No, this is not okay. Any other questions?
All good.
Okay. So with all this cancellation, I'm left with the differential equation v double prime of t e to the t is equal to 0. Oh, you can't see that. When everything else cancels, I'm left with v double prime of t e to the t is equal to 0. Is e of t ever equal to 0?
No.
So I can divide by it. And now what I'm solving, or what I find, so we find that v double prime of t e to the t is equal to 0 if v satisfies this diff eq, then v of t e to the t is a new solution. But this is just saying v double prime of t is equal to 0. And now this is a calc problem. This isn't a differential equations problem. This is saying I've got a function of t whose second derivative is 0. So I integrate both sides once, so I get v prime of t is equal to some constant, and then v of t is equal to c1t plus c2. Exercise for you. Check that t, so here what I'm saying is c1 t e to the t plus c2 e to the t is for any constant, c1 and c2 is a solution. What I'd like for you to check is that t e to the t solves our original differential equation, which is y double prime minus 2y prime plus y is equal to 0. Let me know when y'all have checked that indeed I get a second solution from this. Y'all been able to check that indeed t e to the t solves the differential equation?
Yep.
Yep.
Great. One other thing that we can check together, since I don't want to make y'all do all the work, let's check the Wronskian, right? I mean, this is a little bit of a formality, but we should do it anyways. So in this particular case, we're looking at the determinant of e to the t and then e to the t. And up here I've got t e to the t, and I take the derivative of this and I get e to the t plus t e to the t, if I'm not wrong. Did I take the derivative right there? E to the t plus t e to the t. Yeah, I did. And this determinant is equal to e to the 2t plus t e to the 2t minus t e to the 2t is equal to e to the 2t. Did I do that right? So this is never 0. So indeed, t e to the t and e to the t give a fundamental set of solutions. So in this way, in this very naive way of just demanding that we find some function v such that v times our original solution is a new solution, we produced a differential equation in terms of v that we were able to solve, namely v double prime of t is equal to 0. And then we produced a second solution, which is gives a fundamental set because the Wronskian is non-zero. Not the zero function, I should say.
So wait, Professor, how did you go from C1t plus C2 to C1t e to the t plus C2 e to the t?
Well, because remember that I was looking for, like what I originally plugged in was v of t e to the t, right?
Yeah.
And what we found is we plugged this in and we got v double prime of t is equal to 0. What this means is that anytime I have a function v such that its second derivative is equal to 0, then that function times e to the t will be a solution. Here is the collection of all functions whose second derivative is 0. When I multiply this by e to the t, I get this.
Oh, okay.
And another way of thinking about how I get this family is I can also remember that e to the t and te to the t separately form a fundamental system of solutions. So I know that the arbitrary solution should be c1t e to the t plus c2 e to the t. This was a way of saying all possible solutions where I have some function times my original solution. What are the possible v's? Well, they're all the c1t's plus c2's. And in particular, if c1 is 0 and c2 is 1, I recover my initial solution of e to the t. Is this okay?
Yep.
And you'll be gratified to know the following fact. Whenever we have ay double prime plus by prime plus cy being equal to 0, such that b squared minus 4ac is equal to 0. So we know that one root is equal to e to the negative b over 2a. 2a is, or a solution. What you can check is if you plug in v of t e to the negative b over 2a into, so set this equal to y, plug this into the differential equation. If you do this short calculation, well, short in the sense that it's short, it's like 5 minutes, but I don't have time to do it right now because it's essentially the same calculation that you just did. You'll find that we obtain, or we get, the diffie q v double prime of t is equal to 0. So this means, so thus, if we have a repeated root, if the characteristic poly has repeated root, a fundamental system is e to the negative b over 2a and t e to the negative b over 2a. These two form a fundamental set of solutions. And by essentially the same computation that we together did above, the Wronskian of this pair of functions is non-zero. So this is indeed a fundamental set of solutions. So let me just give you another example to work out pretty quickly now that you know the formulation for this last kind of characteristic polynomial. So find the general set of solutions for y double prime minus 6y prime plus 9y is equal to 0. So what's the general solution here?
C1 e to the 3t plus C2 t e to the 3t.
Yes, e to the 3t plus c2 t e to the 3t, right? The root of this characteristic equation, x squared minus 6x plus 9, the roots here are 3. It's a repeated real root, so the general solution is just this. Okay, so we had to do a fair amount of work to get to this general solution, but now you are well equipped to handle every kind of a y double prime plus by prime plus cy is equal to 0. And it's kind of a funny fact that it took us a reasonable amount of time, maybe 4 or 5 days overall, to solve all of these second-order linear homogeneous differential equations. And these, in a certain sense, are just the very simple ones, the most simple ones where the coefficients are just constant. So nonetheless, we still did a lot of math to get all these solutions. Okay.
So, Professor, when we're going...
Also, just a note, I'm not a professor. Y'all can just call me Mark, so that's fine.
Oh, okay. Well, so when we're going through the homeworks, do you want us to practice like deriving that expression where where we get like basically doing all that work? Or is it okay to take a shortcut and just say, okay, I recognize the form of this equation. I know that the solutions are going to be e to the negative b over 2a and t e to the negative b over 2a.
Unfortunately, the answer is kind of both. And I know that that's not a fun answer, but the point is as follows. On a given test, first of all, I could ask you to literally solve one of these differential equations. Like, there's no way that I'm not going to ask you to solve several linear second-order homogeneous differential equations with constant coefficients. I'm going to ask you that. And if you know the form of the solution for those in particular, then you'll be able to answer those questions quickly and efficiently, right? Like, you see such a differential equation, You take its characteristic polynomial, it's got a repeated root of 3, boom, you're done, right? So at this point, if I have a y double prime plus by prime plus cy, this should be a quick solution for you. I could ask you like, 5 of these in a row on a test, and you should be able to answer them quite quickly because we know the form. But on the other hand, I also am going to ask you some of these more general sorts of questions, so you should be comfortable at least with the ideas of how did we find that second solution. In particular, our next topic that I'm just going to discuss is called reduction of order. And it's exactly the same thing that we just discussed, where if you've got one solution, you should try to find a second solution by taking some arbitrary function v of t and multiplying it by your first solution and plugging in. So you do need to remember that tactic or that technique. But from now on, when you see a differential equation like this, you don't need to derive anything. You can just produce the solution like this. Does that answer your question?
Yeah, thank you.
Yep.
So there's nothing really different about uniqueness or existence in regards to these solutions, right?
No, the uniqueness and existence, which first of all, we didn't prove, we just discussed, but the uniqueness and existence for second order linear differential equations was very strong. The formula that we got was have existence and uniqueness for y double prime plus p of t y plus q of t y prime plus q of t y is equal to 0 whenever, actually for this is equal to g of t, whenever p, q, and g are continuous. Well, here, when they're constants, constant functions are always continuous. So existence and uniqueness already guaranteed us the existence of unique solutions to IVPs, which are defined on the whole real line for all of these.
Mm-hmm. Thank you.
Yep. So existence and uniqueness is actually a very strong theorem, and it tells us information about differential equations that we can't even solve. How much time do we have? Oh, not very much time. Okay, so let me just discuss this reduction of order, which is the same idea that we just went through. Suppose we have a solution. Y1 is a solution to y double prime plus p of t y prime plus q of t y is equal to 0. y1 of t. Well, then once again, we can try the exact same approach and get the following. Let's take derivatives. So we should get eventually, so plug in v of t times y1 of t in for y. And then we get some very messy expression, which essentially looks like this. We get y1 of v double prime plus 2y1 prime plus p y1 of v prime plus y1 double prime plus p of y1 prime plus q of y1 v is equal to 0. So this is what happened after we plugged in and canceled as much as we could. We get this big long expression in terms of v double prime, v prime, and v. So if you don't believe me on this, by all means, check yourself. This is essentially what we get by, yeah. You just plug this into this differential equation, and collect terms until you get there. What is this?
Is that 0?
Yeah, this is 0 because y1 is assumed to be a solution to exactly this differential equation. Y1 being a solution means y1 double prime plus p of ty prime plus q of ty is 0. So actually, this whole differential equation reduces to y1 of t v double prime of t plus 2 y1 prime of t plus p of t y1 of t times v prime of t is equal to 0. What is this?
Can you put the paper up, please?
Oh, yeah. How's that?
Perfect.
This is a v prime of t. My claim, this is first order linear for v prime. If v prime is the function that I'm interested in, then I have a function of t times the derivative plus a different function of t times my function is equal to 0. This looks like this is first order linear for the function v prime. Do we agree?
Yeah.
So we can explicitly solve for v prime of t, since we know exactly how to solve first order linear. Now, an additional question would be, once we have found v prime of t, is there a way to find v of t? Namely, once I found v prime of t, can I integrate it nicely? And of course, the answer is yes, if you're willing to use the first fundamental theorem of calculus. Maybe it doesn't have any sort of nice expression in terms of elementary functions, but nonetheless, this is a process that we can always do for second order linear differential equations. So this is me saying that actually this very naive idea of if I've got one solution to the differential equation, I multiply it by a second function, v of t, which I haven't determined yet. When I plug this into my second order linear differential equation, what I get out is a first order linear differential equation for v prime, which I can solve. So in other words, this idea of trying to find a second solution like this is actually quite flexible, despite it being incredibly naive. And what I was hoping to do is show how this works out, but I think we don't have time today. So yeah, maybe I'll start with start next time with examples for reduction of order. Okay, that's all for today. And have a nice afternoon, and of course, please stay safe.
Thank you.
Thank
Yep.
you.
See y'all tomorrow.
Thank you.
Thank you.
You.